Thank you, Magnus. Thank you, everybody. Also for having me here. We've been working quite a while together. Before getting to this specific issue, I just make a very brief overview of our group activities, mainly on using new nanocarbon and microcarbon filters, innovative ones from mainly from waste and biochar for composites, and working for characterization of carbon materials and other types of composites. In this specific conference, I'm going to discuss a little bit the standard operating procedure. The first part will be quite philosophical, so I hope you will enjoy the conclusion. And then I will focus and try to make a clear example of what I mean by all this philosophical stuff about SOP. So the organization of the talk will be what is the need for SOP, the role of SOP in your projects. They are huge projects, many partners, and sometimes they do not go all in the same direction, so you need to be a bit strict and give some direction. Let's have a general approach to the structure of SOP, and then, in order to make things a bit clearer, I hope, an example, which is, okay, when you collaborate, you know very well, if you are focusing a given analysis, which is performed by several groups, you have to share data, you need to exchange, but you need also to get the same kind of information on the same sample, which is not always guaranteed if you don't really agree on which is the procedure. So the SOP is something which is trying to actually fix this point. And from my point of view, SOP, as you can see, is not only instrument setting and data collection. SOP is up to the end, data analysis and interpretation, because this is the full job when you have to do, and you have to agree on it. In European project, this is more relevant, because you have to define the SOP for each analysis, as a large number of partners are involved, and they might use different procedures, which they might make sense on their own, but they might produce some slightly different output, which you might not be quite easily able to merge. And so you have to guarantee consistency, internal, partnership, external, when you try to disseminate, and of course in reporting, because you're not reporting different stuff on the same kind of analysis, because otherwise it's confusing and it's not very serious for the reporting in the partnership. Okay, from my point of view, as I said, you have a few steps which are common, and of course then you can decline them in details for each characterization procedure, process, and whatever it is. So you need to define the experimental procedure exactly, and if you have an instrument, you have setting parameters should be quite well defined. The collection procedure, the analysis procedure, and interpretation are also to be very well clarified for a SOP that can be shared among partners. The first step is to select and compare instruments. Because if you have different partners, most of the time they do not have exactly the same instrument. So you have to check that they are compatible, they might have different details, you have to check them, and you have, of course, to define a common procedure that every partner can be able to use. Of course, I mean, it makes sense that if you want to go for a more sophisticated investigation, you just focus on the partners that have the most performing instrument. Not everyone is doing everything. Okay, in order to define the instrument parameters, you have to identify the target of measurements. That is the information you're looking for, because following different information, you might want to set your instrument in different ways. If you are looking, for instance, SEM on large scale, you set magnitude is magnification for a given number. If you are looking for more details, you change magnification, so you might change the instrument parameters. And you should be aware of how each instrument setting will impact on the output in order to select and define properly. And once you have learn all about this, you focus on your specific experiment, and you define the best setting. Then you go to data collection. That means you perform measurements and record data. Of course, this is something everybody knows, but sometimes you forget and then you lose your data. So it's some kind of things critical. I told you that I'm going to discuss a very basic philosophy, something that is everyday life philosophy in which you make things the best way without going to very complicated science at this stage. Then you have the data analysis. The data analysis obviously aims to extract the elementary contribution. For instance, is in XPS. You are, of course, interested in the overall signal, but you are interested in the components. So you need to be able to extract the components, which sometimes is easy, sometimes not so easy, because you might not have a very, let's say, widespread agreement on what is actually behind a composite peak. So you have to look through bibliography. I put this strange Latin words because you have to be quite careful in reading bibliography. Sometimes people pick up from bibliography some information they do not refer to their system and say, okay, oh, it's same for me. You have to be very careful, especially in the field of carbon. You have so many different types of carbons and carbon materials that you cannot straightforwardly take an information from one type of carbon and use it to analyze the other. So this is very careful. And also, I mean, nowadays you can publish something going from 0.01 to 50 impact factor. So you have to be quite careful in what you read in order to be sure that you are getting the information which is arriving. And then, if you have to make this kind of analysis and try to find the components, you have to select or develop an appropriate tool. And, of course, you need an operator. Sometimes people say, oh, this technique is very easy. Well, no technique is easy. You have to perform the technique properly. I have been around for infrared, for instance. Infrared is, everybody thinks it's easy. Okay, if you do it properly, it is easy to do, but it's not that I just go there, make my infrared measurements, and I got perfect results. So operators are critical, and of course, this is also critical to have new operators which can perform in the same way. Okay, then the other final step is data interpretation. And here again, you have to be very careful because this is what you are looking for. You don't really want to make measurements, you want to get information. And then you need to make measurements to get information. So again, you have to be reading carefully all the papers. And in the papers, try to look for appropriate reference material, because otherwise you might refer to material which is not exactly your part. And generally speaking, it would be nice that you don't rely on a single characterization technique to have your information, but you can put together many techniques and they give all the same kind of information. They bring you towards the same direction. Okay, now from the general philosophical issues, which are very basic actually, we go for a very specific issue, which is Raman. Okay, I'm not going through Raman more in detail. Raman is quite a widespread technique. We have been working on Raman for carbon, as you say, for the last millennium, so it's quite a long time. And we are quite aware that even Raman on carbon materials is looked at as a standard technique for characterization. It's not as simple as that, because there are a number of issues, especially in disordered materials. And carbon fibers, from the point of view of Raman, are disordered materials, which do not allow to be so straightforward in interpretation of Raman. So here I'm trying to detail how to approach the problem of Raman in carbon materials. And the advantages of Raman are quite well known, because it requires little or no sample preparation. It's a non-destructive technique. You don't need any kind of vacuum system or specific system other than having your clean room. Clean means with no powder, doesn't mean a clean room in the technical issue way of thinking. in principle, it can be used as an online quality test, and is item specific. It can target specific elements, bonds, or structures in a solid. So these are advantages of Raman, for which we have been working on this for a number of years. I will be very brief on Raman effect. Essentially, it's an elastic scattering of photon. You send a photon, you get another photon which has a different energy, which comes out. Then you have two types. One is Stokes, in which the outcoming photon is lower in energy, and the other one is anti-Stokes, in which is higher in energy. They give more or less the same information. We normally focus on this one for a number of reasons, which I'm not going to discuss here. So this is a process. You get a green laser line, for instance, photon, and you have some intermediate state, which is very complicated. I'm not going to discuss it. And you might produce a photon and have less energy for your photon, or you just absorb this photon and get more energy for your photon, which is getting out. From the point of view of basic quantum mechanics, it's two-step scattering process, which is quite complicated calculation. But from our point of view, for the practical use of it, it's quite relevant that Raman and luminescence are quite two competing processes of this excitation, so that you have to be careful when you are investigating highly photoluminescent material, that your Raman might be quite difficult to measure. Which kind of information are you able to get from Raman? Well, the Raman shift is the loss in energy, actually, by the photon, and can be associated to specific bonds, somewhat like infrared. The detail is not the same, but the kind of information is similar. The absolute intensity, you usually don't focus on that because it's too complicated to make your calculation. So we are looking actually on relative intensities of the peaks. So you have a peak position, type of bonding, this information you get the peak position. If you look at the quantitative analysis, you are not looking at the absolute values, but you compare the intensity of different peaks. And, well, one widespread and well-known parameter is ID over IG in carbon materials, which is the ratio between two specific peaks in carbon material. And also interesting thing you have to remember that Raman analysis is actually some kind of volume technique, because it's getting you information in carbon materials down to a few micrometers. So it's not looking at the surface. If you want surface technique, you look elsewhere, not Raman. Okay, this is a typical Raman. You see there are many different elements. Each of them has its own characteristics. Each of them has to be compared when you are comparing with your partners to see if they have a similar characteristic, especially monochromators is relevant, the detector is quite relevant, and all other. I just put this very small because I don't want to make advertisement, but this is a kind of system. Okay, the first one is you have to make the choice of the wavelength of the laser line. You have a laser which is impinging on your sample, and you have to pick up the appropriate laser wavelength. These are the kind of things you have to remember, that the different wavelength will impact on the photoluminescent background, which is something is detrimental to your Raman analysis. So you would like to reduce the impact of photoluminescence. Then Raman has some kind to do with resonance effects, so you have to pick up the proper wavelength in order to enhance the resonance effects. And usually the cross-section of the phenomenon depends on the impinging photon energy. These are all the elements that will have to be considered when you want to define one or more wavelength of your analysis. This is an example of what you get for carbon materials, or when you change the wavelength of laser, and this is a number. This is for typical carbon material. You see that the photoluminescent background, which is this growing up of the background, is reduced highly when you go to infrared instead of green or blue. So this is one thing you can do. If you don't know this, you get rid of it by increasing your wavelength. Then the first step in the SOP, once you have defined your wavelength, is to set the instrument. There are a number of things you have to be careful about, which I have been summarizing here. Each of them needs a discussion and comparison with partners. So you have to fix properly the sample, and you should try to flatten because you have to focus. So if it is not well flattened, you are getting not appropriate quality signal. And then the best procedure is to go for successive focuses and then stop at the one you want. You pick up the measurement mode. There are two different measurement modes which are commonly used. You have to pick up the laser power source in order to maximize your signal to noise ratio, but you have to remember that high power can damage samples. So you have to be careful about not running your experiment with too high power. And then you have to fix the time exposure and accumulations in order to get the best signal to noise ratio again, but to avoid saturation. One of the key points that most of the time is disregarded, but you have to take into account, especially if you have different detectors, is that the detector impacts on the shape of what you get. You see, this is, for instance, a CCD detector. This is a region of the photon energies that you collect when you use a red laser line. This is for green laser, and this is for blue laser. So you see this will be impacting on your output if you don't take into account the correction due to the response. And if you have different response from different partners, you have to take into account, otherwise you will not be able to compare in a proper way the data. This is, for instance, an example. This is graphene material. And you see that if you don't correct for the detector, you are altering the ratios of these two, and so you are getting information which are not appropriate for your system. When you come to data analysis, then first one is you have to take into account the detector sensitivities I just discussed. You have to take into account they are not looking at overall shape, you are just looking at what is over the background. So the peaks, real peaks that you are focusing that come from carbon. In order to look at them and analyze them, you need to pick up the line shapes. You have many different line shapes that go from Rayshard to Gaussian to Bright-Pickett-Fano and others, which you must define on the basis of your system. A number of peaks you want to make the fit. Of course, if you are going to analyze a composite signal, if you put 20 peaks, it would be having a perfect fit. But does it mean anything from the physical point of view? So you have to look carefully on the choice of peak, on the basic of physics and comparison with existing data and your expertise on the system itself, which is based on carbon. When you make the fit, you have, of course, to define a quality check for your fit. And once you have done all of this and you agree always with partners, you can start your data fit and try to get out information on the single components that build up the signal. That's what you are looking for. And one of the key points is background subtraction. You see here you are not interested in the overall signal, but only on this part which is additional to the background. And if you look around, there are some nice / funny things. This is something you get from a commercial software. I'm not going to comment, and I didn't put the name of the software because it's quite evident that it's something that doesn't make any sense. But also when you have something that seems to make sense, actually is not so straightforward, it doesn't make sense. You say, okay, this is nice, this is linear. But you cannot conclude it's linear unless you have a wider range in order to see if it's actually linear on the left and on the right. And so on. There are so many different issues that you have to take. And this is output. This is the same signal recorded, but in which you have made different background choice. You can use the pure Laurentian, which is related to the elastic peak. You can use a linear fit of the background like this before, or you can look more in detail at the physics and get difference. It's obvious that you are getting different information from the same fit if you don't agree with your partners on the best approach based on physical properties of the system. So, first step is get this information by subtracting the background. I would say that this black one is the best one for a number of physical reasons, but this is beyond my interest now. Once you have your spectrum, your peaks, you want to get the single components because they are having the information you are looking for. So the evidence, of course, will help you. There are at least one and two here. Normally it's more than that. But if you have an idea of what is your type of carbon, analysis of literature can help you. Although it should be quite critical. In this field, this is not, from my point of view, totally reliable. Okay, this is the ideal roadmap if you want to plan a good experiment on a new material which is carbon-based. Use several wavelengths, be careful in the choice of the peaks. That is, you have to make the choice about the number and the shape of peak on strong physical basis. Because if you put 50 peaks, you get best fit, of course, but you don't know what they mean. If you have a number of wavelength, you have to be consistent among the different wavelengths. Because you are not expecting that I get an additional peak for one wavelength, it disappears and it goes back, it moves. There should be some physical basis to what happens to these peaks. They may shift and enlarge in some way that makes sense. And if you have a luminescence, okay, you should actually, to be quite ideal roadmap I put here, so you should record the photoluminescence spectrum on its own and use it to subtract. Most of the time you don't do it because it's an additional experiment, but you have to be careful about what is this impact. Okay, from a point of view of peak picking, we are currently completing a couple of experiments because we don't really rely on trust on what is around on disordered carbon materials. So the two is we are performing Raman measurements with 3 different lines on several types of carbon that range from graphene to graphite to amorphous carbon, diamond, and all types of carbon involved in FIBRALSPEC, carbon fibers, and not only. And we also perform treatment up to 2200 degrees in order to follow the evolution of Raman lines. And this is going to provide us with a set, a consistent and reliable set of peaks that we can use for every kind of disordered carbon. Ordered carbon is not a problem. I mean, graphite, graphene, carbon nanotubes, when they are well crystallized, diamond, they are quite standardized. But when you go to disordered carbon, including carbon fibers, including charcoal, including other things, it's not so straightforward. There are much more problems around. Okay, in the end you have the kind of structural information you can get from the Raman spectrum of carbon materials is based on this understanding. I would just want to add one point. The deep peak, it was variables in carbon, is not due to disorder, is not due to ring size, is due actually to the density of edges, which of course correlates with the grain size. If you have smaller grains, you have more edges, but it's not as directly due to grain size, it's due to the presence of edges. And then is the kind of information you have to use in order to get your structural information from your analysis. In order to conclude my talk, he has not yet told me anything about the time, so I think that it's okay.
You should be concluding.
Okay, I will do it. I know you are. If I conclude, other people can come, and so we can eat before the schedule. That's what that's. You essentially have 2 types of SOP in Raman. One is the optics. If you want to be very precise, nice, perfect on your SOP, you use several wavelengths, collect high quality Raman signal, means signal to noise ratio is very high. 2 minutes, thanks. You subtract the baseline, background, with proper baseline libraries. You choose the backspeaks library. Remind that physics is more important than mathematics here. The field signal, I compare different fields using a field quality evaluation parameter. And consider a component history and physical meaning among the different wavelengths signal. Of course, this is optimum. You want sometimes just to share information and to check the quality. So you can go to the minimum, SOP, which is more standard. And so you fix your wavelength on the basis of the previous experiment. You collect high quality Raman signal, you subtract baseline again. Okay, the steps are of course the same, but you are been fixing one single wavelength which makes things much faster. And it is only for quality check and comparison. This is something that works properly. In conclusion, okay, I've been talking about SOP from the doctoral point of view. I want just to point out that SOP has to go from the very beginning to the data interpretation. It cannot just be how I collect the data. You have to go up to the end in order to be sure that you share the same view of things. And this is what you get from the application of SOP to Raman of carbon materials. Essentially what is important is why Raman is interesting, because most carbon materials have some kind of fingerprint. Like in XRD, you have fingerprints. You have fingerprints also in Raman. For disorder materials, it's not so straightforward, but it is quite enough straightforward for all other materials. And okay, I think it's enough from my side. Thank you for your attention.